Good morning, students. I'm Chaitanya, Assistant Professor in Mathematics, Institute of Aeronautical Engineering. Today, I'm going to discuss on what is a bit and what is entropy and what is surprisal. That means which is a important part of the information theory. So we are going to discuss an important topic from fifth module. Now let us look into the details. See, first of all, before going into the details, it is our courtesy to mention the name or to recollect the name of great scientist Claude E. Shannon, who introduced information theory and who introduced entropy and measures of entropy, and which become a game changer in machine learning. So, and also communication systems. Now let us have a look into his brief history. The information theory has been developed in the year 1948 by Claude E. Shannon at Bell Laboratories. He introduced in his paper a mathematical theory of communication. He introduced information theory at the first time. The goal of that is the efficient transmission of information over a noisy network. That means, even though there are several hindrances in transmitting the information from one communication channel to another communication channel, how to minimize those hindrances and how to make the transmission very smooth and efficient. So with that goal, he made research and he introduced entropy measures and which paved the path for information theory. Okay. In this, he defines the fundamental limits on compression needed for reliable data communication. That means, in short, what his research is, in his research, he tells that we cannot go beyond a threshold while compressing the data. If we go beyond that threshold, the essence of the information will be lost. So, definitely there exist some limits which we have to calculate mathematically, and those limits tells us that we cannot go beyond those limit while transmitting the information in order to not lose the essence of information. That is reliable data communication. Okay. Now, so before going to the definition of entropy and surprisal, etc., we must have to recollect what's the random variable and some of its properties. See, a random experiment is nothing but an experiment whose result cannot be predicted in advance. Okay, like if you take tossing a coin or rolling a die or any competitive situation, whether any sports or any games, everything is a random experiment, and every random experiment will be associated with the sample space. Suppose tossing of two coins, it will be associated with the possible outcomes, that is HH, HT, TH, TT. Set of all possible outcomes is called sample space. Now, if you define a function x from S to the set of real numbers, that means any function that is defined from the set of sample space to the real numbers, that function is terminated as random variable. So any real valued function defined on the sample space is called a random variable, that we know. And this random variable transforms this non-numerical sample space into numerical sample space. That is the purpose. Here you could see an example of a random variable where you are mapping the head onto 1 and you are mapping the tail onto 0 when you toss a coin. When you toss a coin, the result, if it is head, that will be mapped onto 1. If it is tail, that will be mapped onto 2. Now, entropy in information theory. What is entropy? First, let us have a look into this. Entropy is the measure of the average information content missing from a set of data when the value of the random variable is not known. That means when you have a data set, say x, y, z, okay, and when you are missing with some data w column, you are missing this column in the data matrix, that is w is not available with you, then you will assess entropy is nothing but the measure of the average information content missing from the set of data when the value of the random variable. That means while you are applying dimensionality reduction or data compression or data reduction processes, you will lose some information. So to measure the loss of information, or to express uh, the loss of information in terms of some mathematical measures, we need a tool which is called entropy. So entropy is nothing but it is a measure of loss of information. Information is measured in bits, bytes, gigabytes, megabytes, etc. Now we are being introduced with another measure which is entropy, which measures the loss of information, not the information, the stored information. It measures how much information you have lost. That is measured and it is terminated as entropy. Okay. It helps determining the average number of bits needed to storage or communication of a signal. That means you have lost this uh, amount of bits of information. If you gain that, you could store. That's what it tells. In simple, you can tell. As the number of possible outcomes for a random variable x increases, the entropy increases. That means as many columns as you have, okay, the loss of when you are reducing as many columns as possible, you are going on reducing as many columns as possible, you are losing the information. That means entropy increases. That's what it is saying. Okay. As entropy increases, the information decreases. That means entropy is nothing but loss of information, the amount of information you lost. So when entropy is increasing means you are losing the valuable information, you are losing the information. So what you understand, the information stored and the entropy both are inversely related. If entropy is more means less information is with you, and if more information is with you means entropy will be very less. That means loss of information is very less. That's what. See example, in MP3 sampled at 128 kbps has higher entropy than 320 kbps MP3. Because if you want to store a video, MP3 video in the storage, your loss of information will be less. But if you want to store the same video in the storage, you have to lose more information. That means you have to compress more. That's what. Okay. So, what are the applications of entropy? Let us have a look. In data compression, that means compressing the videos MP3. Now we are observing MP4. Of course, it is a little older. MP4 to MP3 you can reduce, and MP3 videos you can compress. Okay, those kinds of, and JPEG. That means when you are not able to upload a photo in JPG format, you have to reduce its size. Then you will resort to compression techniques. Those are all where this entropy helps you to go wise in compression, data compression. Okay, and zip files. When you are sending some zip file attaching to email, and sometimes you may not be able to send the mail. Sending may be failed due to large size of zip file. Then what will you do? You will compress the data. So in compression of data also, You have to be very wise. You should not lose essence. Okay, so entropy always helps you uh, to be wise in saving the information, the essence of information. And cryptography, that means, what is cryptography? Cryptography is nothing but uh, data encryption. Data encryption is what I mean by that. Sometimes you must be confidential while sending data from one channel to another channel, because you are sending very very confidential information. You should be very very careful while sending. That means you cannot send the data as it is. You must send it in a encoded form, so encoding will happen. Okay, and the receiver, when he receives, he has to decode, and he has to get the original meaning of the information. Okay, for an example, I'd like to take this thing. I'll give you a small example. uh, Submit the file, submit the LO file, or I could tell you more connective example. Pick the second set as to question paper, as question paper for tomorrow's exam. For tomorrow's exam, that is what you'd like to send a message. That means generally when some competitive exam has been conducted, generally they will prepare more than one set, like say set 1, set 2, set 3. And just a few hours before, the higher authorities will decide which set has to be given to the candidates, because it's a competitive exam. And for the sake of unbiasedness, they will select randomly one set. So when they have to send this message to the examination centers, or what, few hours before or 24 hours before, they will send. How they will send? They cannot send this message in English like this. If they text like this, anybody can hack into their systems devices, and they can read it, and they come to know that this set is going to be really like that. So what they will send this message in an encoded form. That is called data encryption. The process of doing this is called cryptography. I'll give you an example. What is the alphabetical position of P? You know, A is denoted by 1, B is denoted by 2, C is denoted by 3, like that. Okay, M will be 13, N 14, O 15, P is 16. Okay, A, B, C, D, E, F, G, H, like that. Suppose I'd like to write for your convenience. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Now you will encode P as the position. P's position is 16, and what is I's position? Alphabet I is positioned at 9, so it is 9, and C is 3, K is what? K is 11. Okay, and you write T as what is the position? 20. H is 8, E is 5. Okay, and you write second set means you'll write 2, and S means you'll write 19, E means you'll write 5, T means you'll write 20, and you will send A means 1, S means 19, and you will send Q as 17 and P as 60. Now when you send this is called encoding, because you are not sending it directly. You have transformed the original text into some other form, and then you will send this as a message, cipher message to the receiver. Then he will decode by using the same positions, and he will get the original meaning. This is called cryptography, where encryption means this one, and decryption means he will again write the original letter. That is 16 means P, 9 means I, 3 means C, 11 means K. Like that he will decode. That is called decryption. Okay. Here also entropy plays an important role. Signal transmission across a network. As I told you in the very beginning of the lecture, while transforming signal from one channel to another channel, there will be a lot of disturbances and hindrances, and which causes noise in the smooth communication. That means very disturbed communication will be there. In order to minimize that disturbances, you need smooth transmission. For that smooth transmission, this information theory helps you a lot, especially while sending emails or text messages or cell phones or videos, audios. Okay, like data compression. Nothing but shrinking the size of a file or signal, etc. Which helps us to reduce the cost of storage and timing of storage and the space of storage. So many benefits are there with the data compression. Nothing but shrinking the file size. Smaller the data, the size reduces the possible outcomes of associated random variable, thus decreasing the entropy of the data. That means smaller data size reduces the possible outcomes of the associated random, thus decreasing the entropy of the data. Because if you have saved the data in a small sized matrix, okay, then you need not lose much information, and the entropy will be less. Entropy, minimum number of bits needed to encode without any loss in the information while compressing. That means entropy tells you the threshold of the data up to which you can reduce, you can compress, so that you will not lose the essence of information. Lossless if the rate of compression is equal to entropy. So the rate of entropy is nothing but the rate of compression at which you will not losing the essence of the data. Okay, that is what entropy. Signal data transmission. Channel coding reduces bit error and bit loss due to noise in a network. So suppose when you are transforming one signal from one channel to another channel, the coding which you use reduces the bit error and bit loss due to noise in a network. Okay, so this coding is based on information theory. As entropy increases, the likelihood of valuable information transmitted decreases. If entropy is high, that means loss of information will be very low. That's what it's telling. That means the likelihood of losing the information will be. That means entropy is a good number. That means loss of information is going to be reduced. That means entropy and loss of information, okay, are related to each other in a positive way. Consider a signal composed of random variables. We may know that probability of certain values being transformed, but we do not know the exact values will be received unless the transmission rate is equal to entropy rate. Yes. As entropy increases, the likelihood of valuable information transmitted decreases. That means when the entropy is increasing, that means loss of information is increasing. That means you are losing the valuable information. Okay, so you have to maintain a correct threshold so that the loss of information will be less. Okay, now let us look into the measure of information, that is called entropy. Here, information of a content of symbol Si. Suppose Si is a random variable. Okay, then P of Si will be its probability. then if you apply logarithm base 2 and multiply with minus negative, then you will get a number which is called entropy of the information, represented by the random variable s. So entropy is nothing but a measure which is defined as negative logarithm with base 2 on the probability. Okay, if P of Si is 1, there is no information loss. Okay, P of Si is equal to 1 means uh, this will be log 2 P of Si, that is equal to log 2 1, that means 0. Okay, that means there is no loss of information. No loss of information. That's what it is telling. No loss of information. Smaller P of Si has more information as it was unexpected or surprising. Okay, when P of Si is very less, okay, then logarithm will be a negative value, and when you multiply with it will be a positive. Okay, and it tells you that uh, you are with more information, less information has been lost. Okay. So entropy is defined as a weight of information content of each source symbolized by probability of occurrence. Say summation I is equal to 1 to n P of Si log to P of Si. This is the definition of entropy given by Shannon, which is denoted by H. And H is defined as summation I is equal to 1 to n minus P of Si into log base 2 P of Si. Okay. It produces a lower bound in a number of bits needed to represent information with code words. So this gives you, when you calculate H means you will get the lower bound. That means you cannot compress the data beyond this H. If you go on compressing the data beyond this H, you will lose the real essence of the information. So you cannot compress the data beyond the level of H. That's what it tells. So here we are given a small example. Getting of alphabet A is 40%, getting alphabet B is 60%. Then the entropy is, as per the definition, minus 0.4 into log 2 base 0.4 plus minus 0.6 into log 2 base 0.6, that is equal to 0.97 bits. Okay, so you cannot compress beyond 0.97 or 0.97 bits. If you keep on compressing beyond this level, you have to lose the essence of the information. Okay, the maximum uncertainty occurs when all possibilities are equal. That means H will be very high. H will be very high in the case when all possibilities are, that means like 0.5. If this is 0.5, 0.5, then H will be a big number. Okay, that's what it is saying. Now, so here we are seeing some definitions of entropy. First one, Shannon's entropy, which we have just seen, which is a weighted product of probability of I with its logarithm with base 2 and summed up to k. And binary entropy formula is nothing but simply H of p comma 1 minus, that means possible, not possible, success, failure. Only two things. Binary means two. So either happens or not happens. So it is defined as minus p into log p minus 1 minus p into log 1 minus p. Okay. And differential entropy, or in a very continuous thing, we will define the entropy as in the place of summation we'll write integration, in the place of p we'll write f, and here log f of x dx and so on. Okay. Now properties of entropy can be defined. You can understand the entropy is nothing but expectation of minus log of p of x. As per the definition, expectation of x is nothing but summation x into p of x. So expectation of minus x will be summation minus x into p of minus x. Okay. Or so from this definition of expectation of x, e of x, you can understand the entropy as expectation of the negative of logarithm of p of x. Okay, is not a function of a random variable values and is a function of the variable probability. That means here we are defining the entropy not as a function of random variables images. Suppose x is a random variable from s to real numbers. It will have range set. So we are not defining entropy on the range set of x of s. We are defining the entropy on the probabilities of the range set. That's what it is. It's not a function of the values of the random variable. Instead, it is a function of the probabilities of the values of the random variables. That is what it is saying. Usually, the information is measured in bits. Okay, then use log base 2. But because binomial means 2, 0 and 1. So that is why bits means 0, 1. That is why log base 2. But we have another measure also that is called nats. When we use log base c instead of log base 2 in the definition of entropy. Okay, and as I told you already, if the probabilities are equal, then you will get h value will be as maximum as possible. Okay, and it will be 0 when we are very certain. Very certain means you know that uh, what is going to be happen exactly. Generally, this never be a practical thing. In practical environment, we always having uncertainty. So only under 100% certainty, entropy will be 0. Okay, that means you will not lose any information. You are very certain about the outcomes. And joint and conditional entropies are defined here. Okay, of course, I'll give a separate lecture on joint entropy and conditional entropy. Then we'll come to see them. Now I'm just postponing it. We'll discuss it in the separate lectures. Now, mutual information. Suppose x and y are two random variables. The information lost by x due to y or lost by y due to x, that is mutual loss of information, is defined as see I of x comma y means the information lost by x due to y or y due to x. Okay, both will be equal definitely. It will be symmetric. So it is denoted by I of x comma y, and it is defined as entropy of x minus entropy of x given y. That means the difference between the Shannon's entropy of x and Shannon's entropy of the conditional random variable, that is x given y. And I of y comma x is nothing but h of y minus h of uh, y given x. But both will always result same. That is why you can treat it as symmetrical. That is called mutual information loss. Okay. Now, how to model a channel, a communication channel mathematically? Assume that our input to the channel is x and the output is y. Then the characteristic of the channel can be defined by the condition probability distribution p of y given x. If the input is x, what is the probability that output is y? That is called condition probability. By using this function, we are having a probability distribution function p of y given x. So we can apply entropy in order to estimate the characteristics of the channel, communication channel. Okay. There are several algorithms in measuring the entropies. One of them is Huffman's algorithm. Construct a binary tree of codes. Leaf nodes represent symbols to encode. Interior nodes represent cumulative probability. Edges assign 0 or 1 output code. Okay. In the algorithm, it is telling how the hierarchically the branches goes first leaf nodes, then interior nodes, then edges. Construct the tree bottom up. Of course, it bottom to up. We have to understand the diagram. Of course, Huffman algorithm is one of the algorithms which helps us in measuring the information or information loss, that is entropy. Okay, here you can see an example. See here, for getting A, the probability is 25%, for getting B, 30%, C, 12%, D, 15%, E, 18%. Okay, in the binomial code, you have these codes. So then, uh, you will compute the entropy. This is the probabilities, and you will compute and you will construct Huffman's tree, and by using that, you will calculate the entropy of this information, sending this information B, C, C, A, D. That's what this exercise or example is. Okay. Now, so as a part of our lecture, we should, and also it is very much helpful to for the next coming lectures on entropies. We are having a mathematical idea of random variable. So in that course, I'd like to show you some problems on random variables and discuss their solutions. See here, we are having, under this, we need to understand what is a random variable, how we could do mathematics and on a random variable. For that, I'm presenting an example. Okay. Okay. Now let us look into this example. A coin is tossed for 4 times. The player wins rupees 1,000 when 4 heads occurs, and he wins rupees 750 for a triple head, and he wins rupees 500 for double head, and he wins rupees 200 for single head. But on the other hand, if he loses, he has to lose 2,000 rupees. That means if no head occurs. Find the expected gain or profit or loss of the player by using a random variable. So they are playing a game. Here is an organizer. He gives 4 coins to you, and you have to toss the 4 coins. Basing on the results, suppose if out of 4 coins, all the 4 coins are resulting to head, you will get 1,000 rupees from the organizer. If you got triple head, you will get 750 rupees from the organizer, and if it is double head, you will get 500 rupees, and if it is single head, you will get 200 rupees. But unfortunately, if all are tails, then you have to give 2,000 rupees in return to the organizer. That is the game structure. Now let us write it in a tabular form. So according to the game, first, what is the game? Tossing 4 coins at a time. Tossing 4 coins at a time. So the sample space will be HH, HH, and HT, HH, TH, HH, HH, HT, and HH, TH. That is 4 heads, triple heads. Now double heads. Double heads are HHTT, HT, HT, TH, TH, TT, HH, and HTTH, and THHT. These are the 6 possibilities for double heads. What are the possibilities for single heads? HTTT, THTT, TTHT, TTTH. Okay, these are 4 possibilities. Finally, the last possibility is all tails. This is the sample space. Now, he's telling that if you get 4 heads, you will gain triple head you gain and double head you will gain, but all tails you have to lose. So we will denote the gain with plus. Gain will be denoted with gain will be denoted with plus. Loss will be denoted with minus. Okay, this is the confusion we are making, that if we gain, we'll denote the amount with plus. If we lose, we'll denote the amount with minus. Okay, now we'll define a random variable from. We'll define a random variable x from s to real numbers, such that x of x will be the respective amount whether you gain or lose. So that means whether the amount, how much, whether you are gaining or losing, the amount is taken as the image of the random variable characteristics. Then the Venn diagram will be like this. The Venn diagram will be like this. See, first I am writing 4 heads. Then I am writing the triple heads. Then I am writing triple head. Then I am writing double heads with a little space, that is okay. Double heads. Then I am writing single heads. Then I am writing all tails. So I have divided all the events, all the possible outcomes into 4 classes. Now, according to the random variable definition, we have to map them to their possible outputs, that is the amounts. That is, when you get all heads, you will win 1000 rupees. So, all heads will be mapped to plus 1000. And according to the question, when you get triple head 750, double head 500, single head 200. That means all the triple heads will be mapped to 750 and all the double heads will be mapped to 500 and all the single heads will be mapped to 200. Okay. Now you have to lose 2000 rupees if all are tails. So this will be mapped to minus 2000 because I already told you that the loss will be divided by negative. Now we have to calculate the probability of gaining 1000 rupees. That is, how many pre-images are there for this arrow? Only one. So 1 by total elements in S, that is 16. What is the probability of gaining 750 rupees? That is, how many pre-images are there for this arrow? 1, 2, 3, 4. So 4 by 16. What is the probability of winning 200 rupees? How many pre-images 500 rupees? How many pre-images are here? 1, 2, 3, 4, 5, 6, 6 by 16. How many, as well as winning 200 rupees, that is, how many pre-images? 1, 2, 3, 4, 4 by 16. Now, probability of losing 2000 rupees is only one probability, that is 1 by 16. Okay, these are the probabilities: 1 by 16, 4 by 16, 6 by 16, 4 by 16, 1 by 16. Okay, 1 by 16, 4 by 16, 6 by 16, 4 by 16, again 1 by 16. Now, if you write this in a table, that is gaining 100,000 rupees, gaining 750 rupees, gaining 500 rupees, gaining 200 rupees, losing 2000 rupees. The probabilities just now we calculated. Gaining 1000 rupees is 1 by 16, gaining 750 is 4 by 16, gaining 500 is 6 by 16, gaining 200 is 4 by 16, losing 2000 is 1 by 16. Then the expectation E of x is nothing but summation x into P of x. That means 1000 into 1 by 16 plus 4, 750 into 4 by 16 plus 500 into 6 by 16 plus 200 into 4 by 16 minus 2000 into 1 by 16. Then if you simplify the 1000 by 16, 3000 by 16, 4000 by 16, 3000 by 16, 7000 by 16, 7800 by 16 minus 2000 by 16. That means 5800 by 16. So when you divide this with two table, or if you simplify, of course it is positive. Positive E of x is positive means the game expected profit from this game is 5800 rupees divided by 60. This is the expected, because it is positive we are telling gain. That means game is favorable to the player and he is going to gain on an average 5800 rupees divided by 60. So this is the way how we use the random variable. So now that means to model a real-time problem with a random variable and to calculate expectation. Now this in this way you can use random variables to the possibilities of uncertainties in a data, and you can apply entropy to measure the formulas of entropy to measure the loss of information. So this is what I'd like to share with you, and with this I'd like to conclude the lecture. In the next class we'll meet with one more interesting topic and continue to our entropy. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.